Welcome to ELEC142 Semester 2 Problem Sheet 1 Solutions. This problem sheet solution is going to be in 3 sections. So the first section we're going to talk about how we can get information off of a graph of a waveform and how we can then present that in mathematical form, and then how we can sketch a waveform given a little bit of information about its content. Then in part 2 we're going to look at the phasor representation of waves and how we convert between time domain and phasor domain, and how we tell if a waveform is leading or lagging. The final part, part 3, we're going to be looking at a longer example of how we extract information about a wave from a graph and how we can get some useful information from it. So without further ado, let's start. So question 1 asks you, for the sine wave shown in figure 1, find the amplitude, the peak-to-peak value, the time period, the frequency, and the angular frequency. Angular frequency has the symbol omega. It's worth bearing this in mind that this is a lowercase omega. You should be very familiar with the uppercase one. That's what we use to represent ohms, the unit of resistance. So just be aware that if you're using a Microsoft Office product, it will autocorrect that lowercase omega to a capital omega if it's the first letter of a sentence. So if you're writing a lab report, just be aware that what you're saying may change dramatically depending on if it's autocorrected or not. So just something to be aware of, really. So we've got our 2 waveforms, wave 1 and wave 2. So we're going to get all this information from these graphs. So first up, we want to find the amplitude of the wave. So here we're just reading off the maximum value from the vertical axis. To do this, you have to see where the waveform is centered around. So this waveform centered around 0 volts, which is quite handy because it makes our lives a lot simpler. So we can see for wave 1, our amplitude is 12 volts, and for wave 2, it comes up as 6 volts. That's just finding the maximum value and reading it off from the axis. Remember the units, this time volts. Part B, we're asked to find the peak-to-peak values. There's 2 different ways you can do this. You can read off the maximum value that we had before and multiply it by 2, or you can read off the minimum and maximum values from the graph and add them together to find the whole range. So for wave 1, we can see it ranges from 12 volts to minus 12 volts, which is a range of 24 volts. So that's the peak-to-peak amplitude is 24 volts. For wave 2, we knew this went from positive 6 volts, and we can see it also goes down to minus 6 volts. So that gives us a peak-to-peak amplitude of 12 volts. Simple as that. Next, we want to find the time period of the wave. I said in the lecture that the time period of the wave is a section of the wave that you could take, and then you could replicate that to produce the wave on and on and on for as many times as you want. This comes down to how the wave is periodic and it's predictable. And I said that because these waves are predictable, we can manipulate them in more advanced systems such as communication systems. So let's find the time for one complete cycle. What I've done here is I've chosen the maximum value for wave 1, and I just followed it along until I got to a next maximum value. And that's one time period there. And we can see, just reading off from the time axis now, that that's 5 milliseconds. So that's the maximum to maximum points. You can also do it from the minimum to the next minimum, and that would be the same amount of time as well. For wave 2, I've done it from a different position. Here I've gone from the 0 crossing point, one complete cycle, to the next equivalent 0 crossing point. Note that this is where it's the rising edge of the waveform. That's how it's one complete cycle, because you can then just add lots of these cycles together and you'll see that it is the same waveform. You can also do this from the falling edge to the next falling edge, which would be over here. Again, it's the same. It's up to you to use your discretion to choose which you think is going to be easiest to read. So here you can see that wave 2 is actually also 5 milliseconds period. It's slightly harder to see because of the way that PowerPoint lets me draw lines. So don't worry if you haven't got quite this same answer. As long as it's in this sort of region, you're doing fine. If this was an assessed piece of work, as long as you showed where you'd got your values from and they were sensible, you'd get the marks for it. Appreciate that when you're taking information from a graph, it's not precise and that everyone's going to have slightly different answers. Don't worry, the rule is basically show you're working and then you'll get credit for the work you've done. So see, the time period of each wave is actually 5 milliseconds, they're the same. So moving on, next we're going to find the frequency. I've said before that the relationship between the time period of a wave and the frequency is given by this relationship. So the frequency is equal to 1 over the time period. So all I've done is I've just substituted the value that we had for the time period, which was 5 milliseconds, into this equation. And then what I get out is 200 Hertz. And as I said before in the previous slide, I found that the time period of both waves were the same, so therefore they're both going to have the same frequency. If you measured slightly different time periods for each wave, you may have a slightly different frequency answer. Again, don't worry, as long as you've shown you're working, you'll get credit for your work. I also said in the lecture that the standard units for Hertz are actually seconds to the -1, and you can see this quite clearly from this equation. So we've got our frequency and it's 1 over seconds, so that's where we're getting seconds to the -1 from. Next up, we're going to calculate the angular frequency, and that's found by the relationship of omega is equal to 2 times pi times f, where f is the frequency in hertz. So if you've got an answer in kilohertz, make sure you convert it to hertz before you put it into this equation, otherwise you're going to get an answer that you wouldn't expect. So all I've done is I've just substituted my frequency value into the equation, and what we then get is the angular frequency, which is 1256.6 radians per second. There's not really an easy way to remember these units, it's something that you just know with practice and it just becomes second nature to remember. There's a link to a phasor diagram I put up on Vital that actually shows what omega is, and if you have your phasor diagram, omega is the rotation speed of that phasor for a sinusoid. So have a look at that and it might help you realise, because it's radians per second, it's due to the speed of an angle that's changing effectively. Just a side note here as well to say you should always give units with your answer. If you don't, your answer doesn't make sense. I've said as a note, you will be penalised for this in the exam. Don't throw away marks when you've done the hard work by doing the calculations. Make sure you add your units. It's good practice to get into, and when you go into industry or further study, if you don't give units, your work can get very confusing and people won't necessarily know what you're talking about. It can cause massive problems. So get into the good habit now and it will put you in good stead for the future. So the final answers for question 1. It seemed like it took us a little while to do that, but don't worry, it's a pretty comprehensive view of how to read stuff from a waveform. So for wave 1, you should have an amplitude of 12 volts, a peak-to-peak value of 24 volts, a time period of 5 milliseconds, a frequency of 200 Hertz, and an angular frequency of 1256.6 radians per second. For wave 2, the amplitude is now 6 volts, the peak-to-peak value is 12 volts, time period of 5 milliseconds, frequency of 200 Hertz, and an angular frequency of 1256.6 radians per second. Next up, question 2. Now you've been asked for the waveform shown in figure 1, state which waveform leads the other. So there's two things you need to work out to answer this question fully. First of all, you need to work out what the phase separation is. So that's the difference between the same point on the different waves. And then you need to see if this is a lead or a lag. And that's how we know if it's a positive or a negative phase difference. These differences can be quoted in radians or in degrees, depending on the format you want to do it in. The way to find it in radians is that you look at the difference on the horizontal axis. So we know that one complete cycle of a wave takes 2 pi. That's that length, essentially. So therefore, half of that, which is half a cycle, is pi. Half of that again is pi by 2, and half of that again is pi by 4. So these all apply from this point on the waveform. It's just that I've had to move them down so you can see what the lengths are. Again, these lengths are not quite perfect due to the nature of using PowerPoint to show you this, but I can do it to give you an idea of what's going on. So we can see that this separation between the two same points on the wave, by the two same points, what I've done here is I've just chosen the maximum values. So the maximum value on wave 2 to the maximum value on wave 1. I've come down and we can see that this separation is equivalent to pi by 4. It's one of these things, you just need a bit of practice to get used to it, and then you can probably do it by sight for a lot of them. So that's found us our separation, which is pi by 4. We could have done the separation between the minimum and the next minimum, or the 0 crossing points rising and the 0 crossing points falling on the two waves. It doesn't matter as long as you've chosen the equivalent point on each wave. So that separation is pi by 4, which is equivalent to 45 degrees. That's the first bit done. The next bit we have to do is work out which waveform is leading the other. There's no one right way to do this. The method I use is I look at the 0 crossing point here, so I look at time is equal to 0, and I see which waveform has peaked first. So what we can see is this is actually falling wave 2. So the peak of wave 2 would actually be somewhere along here, whereas this is the peak of wave 1. So what we can see is that wave 2 is leading wave 1, because that would reach its peak amplitude at an earlier point in time, so it's leading. So what we can say is that wave 2 leads wave 1 by our separation, which was 45 degrees, or we could say that wave 1 lags wave 2 by 45 degrees. Just getting used to this idea of leading and lagging and positive and negative phase shifts. So a leading phase shift is a positive one, and a lagging phase shift is a negative one. So now we've done that, all this information we've gathered so far is going to help us answer question 3. So you're asked for the sine waves shown in figure 1, write an expression for them in the form v of t is equal to v max cos of omega t plus phi. So this means it's changing in time. So the voltage with respect to time, lowercase t, is equal to this equation, and this t is the same as this t, so we can calculate the instantaneous voltage at any point in time because we just put our value of t into here. We actually have lots of this information already. So Vmax is the amplitude. It's not the peak-to-peak amplitude, it's just the peak amplitude. And then we've got our trig function. This could be sine or it could be cosine. It depends on what you're doing. Sometimes you're asked for it in a different form, but as we go on to answer more of this problem sheet, you'll see that it is also quite easy to convert between the two. It's just because a sine wave is just a cosine wave with an extra phase difference. Omega we've already calculated, that's the angular frequency. T we don't need to do anything about, we just leave t in the equation. And then we've got this term here, plus phi. This is actually the phase angle, so this is how much the wave is leading or lagging compared to the pure cosine that we've based our waveform equation on. So all we need to do is put the values we have for each wave into this form. So wave 1 of t, we knew that the amplitude was 12, so I've just put that in. And now we need to compare it to a cosine. And I've also put in the value of omega, which was 1256.6. The t is still there. What you need to do now is we're going to look at what it is compared to the pure cosine to work out the phase difference. So you can see for wave 1, it's at its maximum at t is equal to 0. That means it already is a pure cosine. So because it's a pure cosine, we don't need to have a phase shift. So this term, it would be plus 0. Because it's plus 0, we just ignore it. So that's our expression for wave 1. For wave 2, the amplitude was 6. Cosine term there, we've introduced our omega value just here. Then we've got t, and it's plus 45. Where did this come from? Well, we discussed in the previous part of the question that wave 2 led wave 1 by 45 degrees. Because wave 1 was actually a pure cosine, we can just introduce the plus 45 there. And that's where we got that from. So as we can see, wave 2 is a cosine with a plus 45 degree phase shift. So that means it peaks 45 degrees before the regular cosine would. There we go. That wasn't so difficult, I hope. I hope you've been following all of that we've done. You could also present this term as a pi by 4. It's just convention that we're using degrees because when we go into phasor form, this is what we use, and it's making things a bit simpler before we go into that. Right, now last question of part 1 of our solutions. This is a little bit different. Here we're being asked to sketch a sinusoid. So we're told a sinusoid has a value of 0 volts at 2 milliseconds with a positive rate of change, reaching its peak value of 5 volts at 6 milliseconds. So A, sketch a waveform over the range 0 to 20 milliseconds. B, indicate clearly when the waveform is 0. And C, indicate the peak, positive and negative values. So what I've done here is first of all, I've drawn my axis. So I know that it's got a peak value of 5 volts. So I've gone from 5 volts down to negative 5 volts because that's going to be our full range. Then I've drawn my horizontal axis. I've started at 0 and I've gone all the way up to 20 because that's what I was asked for in the question. I've added labels to my axes. This is really important. This is another way students throw away marks, is by not labeling their axes with units. Don't do it. You're doing the hard work. Make sure you do the easy little things that means you don't drop marks. It can make all the difference between a pass and a fail and a grade boundary. So yeah. Just do it, please. So next up, what I did was I indicated where the 0 crossing point was. So I knew that this was 0 at 2 milliseconds. So this is 2 milliseconds. Here's our 0 point. I've been told it's a positive rate of change. That means the wave is increasing. So I started here and drew up and up and up until I got to my maximum value of 5 volts at 6 milliseconds. So I just drew that part of the wave. And once I did that, I knew that it took 1, 2, 3, 4 milliseconds to go from the 0 crossing to the maximum. And because it's a periodic repeatable wave, that means that it's going to be another 4 milliseconds before it's back down to the 0 crossing point again. So that's what I did. I drew this down, and in 4 milliseconds, we got to the next 0 crossing point, which was then at 10 milliseconds in time. And all we did was just then repeat it to go down. So it's going to be another 4 milliseconds before it's at the minimum, and another 4 milliseconds before it's back at the 0 crossing point. And using this, I just extended the values from 18 milliseconds up to the full range of 20, because it's going to be halfway up at that point. And then I extended it back the other way in a negative direction from 2 milliseconds back to time 0. This isn't a perfect sinusoid shape, you'll notice. All you need to do is give an indication of what's going on. The key here is it says sketch. A sketch doesn't have to be perfect. As long as it's clear what you're trying to show, you'll get the credit for it. So there we go. Next, you're asked to indicate clearly when the waveform is 0. I've just gone along, I've said it's 0 at 2 milliseconds, 0 at 10 milliseconds, and 0 at 18 milliseconds. It's just quite simple, just make sure it's clear. And then finally indicate the peak positive and negative values. So 5 volts is the maximum and -5 is the minimum. And I've just labelled clearly those points within the time range. This dashed line across here is not part of the answer. I just drew that as a guide, so when I was sketching my graph, I knew where I needed to go to. So there we go. That was part 1 of the problem sheet solutions. Hopefully you got a lot of those. If you've got any specific problems, let me know and I can give you specific help on a one-to-one basis.